Okay, imagine this. Almost 16,000 critical test results, data that could genuinely save lives, just missed. Why? Because the software, simple spreadsheets, hit a hard row limit.
That was Public Health England during the COVID pandemic. And yeah, the culprit wasn't some super complex technical failure. It was just using basic tools for a massive industrial scale problem.
Right, and it perfectly sets up what we're diving into today, doesn't it? This constant issue where the sheer volume of data, big data, just runs rings around older tools.
Exactly. It highlights why data science isn't just messing around with numbers anymore. It's become this systematic, professional blueprint. You need a proper process if you want results that actually work, that scale, and are reliable.
Okay, so let's unpack that blueprint. Our mission here is to look at the crucial prep work, that rigorous framework, and ultimately the kind of predictive power that really separates serious data science from just, well, amateur analysis.
And we really have to start by facing the facts about tools like spreadsheets. They're everywhere, sure, but they have some serious limitations.
Like what specific, I mean, everyone uses them.
Well, scalability is a huge one. Users constantly report them, lagging, freezing, sometimes just crashing completely when files get over maybe 5 megabytes. Or if you're dealing with, say, over 100,000 rows.
Which sounds like a lot, but in today's world, it often isn't, right? And it's not just the size, is it? There's the accuracy issue, too.
Oh, definitely. Studies have shown the average error rate in spreadsheet formulas is surprisingly maybe 1% to 2%.
That doesn't sound too bad on the surface.
But think about it. If you've got 16,000 records, like in that Public Health England case, a 1% error rate means 160 flawed data points. And that's before you even start analyzing. You could have hundreds of errors baked in from the start. Simple things like hard-coding numbers or just logic mistakes.
Okay, so that flawed input. That leads us straight to the foundation of any decent data project, right? The pre-processing stage.
Absolutely. You simply cannot escape that old rule. Garbage in, garbage out. Raw data, it's just inherently messy. It's full of noise, missing bits, inconsistencies.
So if it's that messy, how do professionals actually clean it up? Doesn't trying to fix every single typo and fill every gap just become overwhelming?
It can seem that way, but they break it down into manageable chunks. Think of it in two main steps. First is standardization. This covers cleaning and integration.
Okay, what does that involve?
It means fixing typos, filling in those missing values. Maybe you use the average price if a price is missing, for instance. And it's about making sure data from different places like separate databases or flat files all get merged together consistently. They need to speak the same language, basically.
Right, getting everything uniform. So once that's done, what's next before you get to the actual modeling? Is the sheer size still a problem?
It definitely can be. And that brings us to the second big step, optimization. This involves transformation and reduction.
Transformation and reduction, how does that work?
Well, reduction is about shrinking the data set down. We call it dimensionality reduction. You're aiming for a smaller version that still holds the core meaning of the original data.
Makes sense. Less data, faster processing.
Exactly. And transformation is key too. You often scale the numerical data, maybe so all values fall between 0 and 1. Normalization, we call it.
Why do that?
It stops the algorithm from, say, thinking a big number like a sales figure is automatically more important than a simple yes-no flag just because the number itself is larger. It levels the playing field for all the inputs.
Wow. Okay. So preparing the data alone is pretty involved. You can't just rely on one person's gut feeling or memory for how it was done. You need a standard guide, right? Is that where CRISP-M comes in?
Precisely. CRISP-M, the cross-industry standard process for data mining. It's a framework that ensures projects are, well, repeatable and reliable no matter what industry you're in.
And it has distinct phases.
Yes, 6 phases.
Yeah.
It starts with understanding the business need, then understanding the data, preparing the data, which we just talked about, then modeling, evaluation, and finally deployment. It provides that essential roadmap.
Okay, so you follow the roadmap, you build a solid model, you deploy it, and then comes the real payoff, right? Moving beyond just looking back.
Exactly. You shift from descriptive analytics, just telling you what happened last quarter, to the really valuable stuff. Predictive analytics, figuring out what might happen next, and even prescriptive analytics, suggesting what actions you should take.
And we see this impact everywhere now.
Oh, absolutely. Think about retail or entertainment. Netflix uses something like 1,300 different recommendation clusters based on viewing habits and metadata. It's a huge part of their growth.
And Amazon.
Amazon reportedly generates something like 35% of its annual sales through its recommendation systems, all built on predictive models.
It's not just retail, though. Finance uses this heavily, too, right? For risk.
For sure. Detecting fraud is a big one. And there's a case study where a large retail bank cut its customer churn by 15%. How? By using predictive analytics on customer behavior to see who might be about to leave.
That's a significant saving. And in healthcare, the impact is even more profound.
Definitely. Pfizer used AI and machine learning to help manage their massive COVID vaccine trial, something like 44,000 people. It helps streamline the whole process, accelerating discovery. It really shows the life-saving potential.
So the core takeaway here seems clear. Success today, whether it's recommending a movie or developing a vaccine, isn't just about having data. It's about applying these rigorous professional processes to clean it, structure it, and model it effectively.
Right. But let's push that a bit further. If we connect this to the bigger picture, once you've deployed one of these predictive models, how do you really know if it's successful?
You mean beyond just checking if the model's predictions are accurate?
Yeah, exactly. Accuracy is important, of course, but real success has to be measured by its quantifiable impact on the business. Did it actually reduce costs? Did it increase conversion rates? And maybe just as crucial, did the people who are supposed to use it, the end users, actually adopt it and trust the analysis?
That's a great point. If the sales team ignores your fancy new lead scoring tool because they don't trust it or understand it,
Then the project has essentially failed, hasn't it? No matter how accurate the algorithm is on paper. Adoption and trust are key.